slide. So I got a blank slide there, and if you want to draw this in here, feel free. I mean, don't waste a lot of time doing it, but the point's fairly simple and straightforward. And this goes back to Joule and what I mentioned on Wednesday or Friday. Joule was one looked at this and said, okay, if you have a falling weight that's turning a gear and agitating water, the temperature of the water will change. And this is where we got this mechanical equivalent of energy. So looking at this and this is where we're getting that mechanical equivalent of energy. But here we're doing it in an adiabatic manner, totally insulated. So the assumption here is there's absolutely no heat entering the system or leaving the system from the outside, from the surroundings. So it's a totally insulated system, adiabatic. So we do this and we get a certain change in temperature. We input through an electrical coil the exact amount of work equivalent to the falling of this weight, over whatever distance that weight fell. We get that in a energy term and input that amount of energy into the water through an electric coil, again in a totally closed insulated system. Delta T in this case equals this. Here's where we're getting that mechanical equivalent of energy. All right, so here's where we go, hey, well, you know, wait, this is work, but I could, and it changes the temperature of the water. This is just energy, electrical energy. It changes the temperature of the water, same amount. If I put the same amount of energy into this. Okay, now just go back to this situation here and tear the insulation off of it. And we're agitating this water with the falling weight, same distance, same amount of work is being put into this water. But what's happening, we find that the delta T in this case is less than these other two. Less than. Okay, why doesn't the temperature change as much under these conditions? Well, something is being lost from the system while we're putting this work on, doing this work on the system. Something is being lost. And so this is just a way to kind of start thinking, hey, there's two things here. There's work and there is, there's heat being dissipated out of here. So we've got these two parameters. We've got work and we've got heat. And so here's where the first law of thermodynamics is coming in, that U, internal energy, I'm going to lay this down. Internal energy is equal to the sum of the heat and work. So there's two things here that are contributing to the energy, the total energy of this system. All right, so that introduces this, and that's the first law of thermodynamics. The internal energy is constant, and it is a sum of those two things. Now this is this is figure 2 out of the book. I'm going to lean heavily on the book. As far as I'm concerned, if you can grasp 85% of the book, we're fine. And there's some places, like in chapter in chapter 1 where they some of these series equations. I'm not going to lean heavily on them. If there's some concepts that we're not going to dwell on, we're not going to worry about too much, 10 or 15% of some of these chapters. So I'm going to track down through the book here pretty carefully, and this is what we want to grasp, is what is in there. Figure 2.2. So if a piston moves out, so we've got this frictionless piston. And there's an external pressure pushing on a certain volume of gas at a certain pressure. If the gas expands, it is pushing against that external pressure and doing work. The system is doing work on the surroundings, in that external piston. The work is negative. It's decreasing the internal energy of the system. The work done contributes to a decrease in the amount of energy of the system. If the piston moves inward and is compressing the gas, all right, the surroundings is doing work on the gas, and it's contracting that gas, and the work is positive. It indicates the work done on the system contributes to an increase in the amount of energy of the system. Okay, these are just some of the points in the book that I think are important. Okay, they introduce an idea here that a lot of processes, most processes don't proceed this way, but they're saying if you can proceed in many, many, many little steps, an infinite number of little steps, so that you get through this change incrementally, very slowly. You can do a process in a reversible fashion. So there's reversible, irreversible. Reversible process is making a change in infinitely small or very small. They don't have to be infinitely small, but very small steps, allowing the system to stay in equilibrium. So, yeah, if we go back to this picture, imagine let's imagine doing this two different ways. One way, just really abruptly, bam, pushing that piston up there. What happens to pressure? Well, pressure eventually will get back to some final pressure. But momentarily, if you bounce that up real fast, the pressure here is going to be real low. The pressure is going to be low here. It's going to be close to the initial pressure down here. You're going to create a whole lot of turbulence in there as this gas comes back to equilibrium. You follow me? If you do it very slowly, if you just move that piston on up very, very slowly, the pressure more or less never gets far away from one uniform value throughout the whole gas volume of gas. So that's kind of the difference here, and that turbulence and all whatever's happening molecularly, really complicates the situation. And so you can simplify it by saying, okay, let's do it very slowly and keep it at equilibrium. Let it adjust to a new equilibrium, all the way up there. And it never really gets away from equilibrium. So that's doing it in a reversible manner. Isothermal, just to throw that in there, we're doing it at a constant temperature. So if you had a system and you submerged it down into a body of water, a container of water, and you had the water at a certain temperature, you could carry whatever you're doing isothermally. All right, so these, and I've included some of these equation numbers here, key equations. There is a reversible work that you can calculate, and it's derived. You finally get down to equation 2.7, negative nRT times the log of the final volume over the initial volume. This is for an isothermal reversible change for an ideal gas. And you can also use Boyle's law then. You can use Boyle's law to figure out what the initial and final. You can use this equation by using Boyle's law to figure out what the initial and final pressure are of the gas undergoing that. All right, so let's just apply that equation to this example. The gas in a piston chamber kept in a constant temperature bath at 25 degrees C expands from, so VI equals 25 milliliters, VF equals 75 milliliters. Very, very slowly, as illustrated there. If there is a 0.001 moles of ideal gas in the chamber, calculate the work done by the system. So reversible work is negative nRT times the log of the V final divided by V initial. And you can use 8.314 joules here. And what answer do we get?
Negative 2721.
Joules? Okay. So that's just applying that one equation. Wait a minute. What do we got?
Yeah, I got negative 2.72.
I forgot to multiply by moles.
All right. Yeah, so we got is it 0.00? Yeah, 0.001 moles. And the volume changes will, if it is expanding, you get a positive for the log of the VF over VI. If it's contracting, you're going to get a negative in terms of the log of the VF over VI. Wait a minute. We are, what are we doing here? We are expanding. Okay. Yeah. We are expanding. I saw this, I thought that was the end product, but no, that it is expanding. So we get a positive times the negative for the original equation, and the reversible work is negative. So yeah, the system is doing work on the piston and it's losing energy. Okay, this is a familiar equation from Gen Chem. Again, heat. Here's heat. equals the mass times the specific heat times the change in temperature. We're going to start getting into, well, okay, so here's just calculating the heat for heating up or cooling down anything. You got specific heats in joules per gram Kelvin for various materials. This is the intensive property. Doesn't matter the amount of material. This is the fundamental property of these materials. Water, liquid water. Yeah, here's liquid water. 4.184 joules per gram degree Kelvin. In calories, water is 1 calorie per gram degree centigrade, or degree Kelvin, whichever way you want to state it. So you got your conversion factor right there, 4.184 joules per calorie.
Why didn't they make that one? Like when they were making this, why didn't they base it off water?
Well, they did in calories.
Oh, okay.
They did in calories. So not in joules. So I don't know. I guess maybe before joule was the SI unit. They did initially make that one and index everything off of water that way. Good question. All right, we won't dwell on that. We won't do a calculation there, but you will have a homework assignment where I'm going to have you compare amount of heat it would take to melt something versus make something. So you'll have to fall back on this equation to do part of the problem, and enthalpy to do the other part of the problem. And delta T here doesn't matter whether it's centigrade or Kelvin, really. I mean, these units are in Kelvin, but the centigrade and the Kelvin degree are the same size, but on a different scale, Kelvin being your absolute scale. So a change in temperature is going to be the same number of degrees, whether you're running off of a Kelvin or a centigrade thermometer. Okay, now heat capacity is an extensive property that includes the amount of material. So you get a very similar equation here. Q equals C, the heat capacity, times delta T. So the heat capacity is the specific heat and the mass of the material combined. So you have these heat capacities and specific heats. So just, well, it'll get a little bit more complicated at the end of the chapter because we'll start talking about constant volume heat capacities and constant pressure heat capacities. So we'll need to make a shift or expand our thinking there in a little bit. There's a question at the end of the chapter. It says citrus farmers, if they know there's going to be a freeze, not a hard freeze, not a hard freeze like this, but a mild freeze, let's say 28 or 29 degrees, they'll spray the orange crop down in Florida. They've had frost come in, a mild frost, and it might be when the orange trees are blossoming, and they know, man, those blossoms freeze, we've lost our harvest. And they spray it with water. They'll spray their orchard with water the night before that frost. Why are they doing that? There's a question at the end of the chapter asking, why would citrus farmers do that? So they know it's going to go down to 28 degrees or 29. They're going to go out and water all their trees and blossoms and all that sort of thing to protect it from the frost. What's going on there?
The water's freezing instead of the planet.
Yeah, so the water is water. It's got to be above 32 degrees Fahrenheit. They spray it on the plant. The mild frost comes in, and it's converting that water to ice. But it's going to take a while for that water to convert to ice. And that ice will not go below 32 degrees Fahrenheit until it's all ice. So it's actually that heat capacity of that water is taking the cold instead of the flour. And if it's a mild frost, all that water may not even, it just kind of gets slushy and then maybe melt again and flowers are fine. The other thing that you got going for you with plants, think about what happens when you dissolve something in water. What happens at the freezing point?
It goes down.
It goes down.
Grant?
Down.
Down?
Goes down.
Goes down.
That's right.
You dissolve any, Ryan,
Goes down.
you dissolve anything in water and it lowers the freezing point.
It raises the melting point.
Yeah. Yeah, it raises
Boiling point.
boiling point.
Boiling point, yeah.
Yeah, raises the boiling point, lowers the freezing point. So you really don't freeze at 32 degrees. I mean, you've got stuff in your bloodstream. Got all kinds of stuff in your bloodstream. Likewise with the plants. They don't just have pure water in them, they've got stuff in them. So their freezing point is down there a little bit, and you can protect it. Well, let's just talk through this one. A sample gas changes in volume from 4 to 6 liters, so it's expanding against an external pressure of 1.5 atmospheres. It absorbs 1,000 joules of heat. What is the change in the internal energy of the system? All right, so here we're calculating this PV work. It's expanding against an external pressure of 1.5 atmospheres. It's changing that volume, final volume, initial volume. So the pressure times the volume change, and you got liters atmospheres, converting it to joules, negative 304 joules of work that the gas is accomplishing against the surroundings. So the system is losing energy. The change in internal energy is the sum of the heat and the work. So we got 1,000 joules minus the 304 joules of work that the gas did. And so the change in internal energy, 696 joules. Yeah, so the heat and the work have opposite charges here. The system is absorbing, it's adding 1,000 joules to the system. It's losing 304 joules doing work on the surroundings, presumably a piston.
So why is it absorbing this heat?
Yeah, that's a good question.
Are they
It is
saying that?
expanding. It's expanding, and you would think it's going to cool. Right. So, and there's another problem, another example they give you similarly, and I don't know, all I can kind of assume is these are two separate things going on. The gas is expanding, but it's also absorbing this energy. So, yeah, you would think it would, as it expands, it cools.
So are we supposed to assume it's isothermal and that's why we're solving it with the arc? Or?
When you're taking in the work, right, that minus 304, wouldn't that be the energy lost to the surrounding?
Well, the energy lost by the system. It's doing this work.
The piston.
Yeah, it's doing the work on the piston, let's say, if that's a... okay, Grant, you're saying it's undergoing this isothermally?
I was just curious because since it's like absorbing energy since we've had 696. Well, it seems like it is since it's expanding. but then we're only taking into account the part that we're losing, but we're still saying it's gaining.
That could be the case. I mean, you'd expect it to cool, but if it was in a heat sink of some sort, so it was doing it isothermally, that's where it could be getting that energy. Yeah,
So
so
if
the
it-
example is, I don't think they've said everything that's going on here. They're just saying, here's the net result that's happening.
If it was
Expanding
not
absorb.
gaining the 1,000, then would we say that it dropped by 304 joules and we could get that to like a temperature? At some, I don't know if we just.
That's
learned that
still the
equation, but-
work. This isn't the heat, this is
Okay.
the work.
I guess I'm trying to understand like how
Yeah.
you like think about them and how they will.
That's a really good question. I mean, if they left that out of there and you said, okay, what's the final temperature of this system, something like that, that would, let's not just kind of dive into it, but that'd be
Yeah.
a possible problem to look at.
Why are we trying to find the change in the internal energy when we're using the pressure of the external pressure? Because pressure of the external is 1.5, but we're trying to find the change in the internal energy.
We're looking at how much pressure is being pushed like on the system,
Yeah.
and the system has to overcome that pressure to expand.
Gotcha.
Yeah, that's what it's pushing against. And so U is Q plus work. And yeah, what is the work? It's working against that external pressure to
Oh,
do this
okay.
expansion. We don't know the internal pressure. Yeah, we don't. So, yeah, so this is PV work, and it's pushing against that external pressure. All right, in an insulated system, Q would be 0 or adiabatic, so delta U would be delta U is Q plus W. If Q is 0, then delta U is just the work. And the author is just telling us, you need to kind of keep track of what the situation is and if there are any restrictions being applied. So you have to ask yourself the question, is this equation appropriate in this particular case? So there'll be a lot of these equations. Okay, this is similar to getting back to state functions. This is a similar slide to what I said a while ago. It's right in the book, looking at two routes up here. And if we look at altitude, it's immaterial which way these two climbers went. Their change in altitude is the same. So that's your state function aspect of it. Whether they went right up the side of the mountain or wound around the mountain, what path they took went up there is material, but it's not a state function. It's a path parameter and not a state parameter. I've got a quick little drawing here, and I got a personal experience with this. I don't know how many of you got out and looked at Table Mountain in Cape Town, but if you look at it from the ocean, it is a table. If you drive around the side and try to climb up it, which a group of us tried to do, we did not realize that we were climbing up an intermediate hill on the back of that mountain. And when we thought we would be back shortly after lunch, we almost got hung up on top of the mountain overnight. We got the last cable car down off the mountain. So here's the cable car side of the mountain. Here is this. You've got climber 1, climber 2. They get to the top of the mountain. They get to the same altitude. That's fine. But if climber 2 goes up a hill, down a hill, up another hill, which climber did the most work? Climber 2 is doing a whole lot, and I know by personal experience, Climber 2 is a whole lot more work. We were climbing for about 6, 8, 9 hours to get there. So that's a path sort of thing. And so work and heat are not state functions. They depend on the path you take to get there. All right, so integral of dW, change in work is W, change in heat is Q, change in internal energy, delta U. The author makes these points here. Delta U is the final internal energy minus the initial. But the W is, change in W is not the final minus initial. You don't really know those numbers. So du equals dq plus dw, delta u equals q plus w. And the author is making a point to, well, he says he's making a point of using capitals for state functions and lower cases for path-dependent functions. But I see pressure with a little p a lot in there too. So I don't think he does that all the time, but he says that generally speaking we're going to look at state functions as a capital and path-dependent functions with a lower case. Well, it's kind of interesting that you got a state function here, exact differential for this, that's the sum of two functions that are not exact differentials. But that's our fundamental equation now for internal energy. The change in internal energy is equal to the heat plus the work. These are some examples again from the book, indicate which state function is equal to the heat for each process described. The ignition of a sample in a bomb calorimeter. Samples are burned for heat content analysis. Okay, so the bomb calorimeter is a constant volume system. Therefore, the heat generated by the ignition of the sample equals delta U. There's no change in volume, so the pressure volume work is going to be 0. So the heat generated is going to be Q. Delta U is going to be equal to Q, because work is equal to 0 as the volume is constant. Melting an ice cube in a cup. The cup's exposed to the atmosphere. It's subject to the usually constant pressure of the air, and so the heat of the process is equal to the delta, the enthalpy. Well, we didn't introduce enthalpy yet. We need to get to enthalpy. All right, enthalpy, not the same as internal energy, but certainly closely related. Cooling down in the inside of a refrigerator, again the volume remains constant, so that amount of heat, amount of energy associated there is going to be heat. Fire in a fireplace, exposed to the atmosphere, it's a change in enthalpy. Let's see, where did the slides go on delta H? So delta H what equation is that in the book? Okay, yeah, page 36, where H equals U plus PV, enthalpy equals internal energy plus pressure times volume. And the author works down through that with
Are you looking for the enthalpy equation?
yeah, he's working it. Well, yeah, if you start in putting that U is Q plus W, you can get to the point where at constant pressure, the enthalpy is the heat. And he's putting that Q with a sub P as, so at constant pressure, this equation simplifies that the enthalpy is the heat. And most chemical reactions are being conducted under constant pressure conditions. You got a beaker and you're reacting something together at atmospheric pressure. Pressure basically does not change. So that is very common laboratory situation as you're working against a constant pressure. And enthalpy is an easier energy term to get to than internal energy, than U. So H is easier to get to experimentally than U. And so this is why we work with enthalpy so much better, even though internal energy is a little bit more fundamental property of the material. Enthalpy is a more practical aspect of the energy that you can work with. So yeah, this is a critical point, because then we're going to be looking at enthalpies, standard enthalpies of formation of various compounds, all going back to these fundamental delta H's. And that's kind of the basis for why we do this. So enthalpy ends up being practically a better term to be working from. All right, we can calculate, in many cases, can calculate all these things. So here's an example again from the book. A piston filled with 0.04 moles of an ideal gas expands reversibly. Expands from 50 milliliters to 375 milliliters at a constant temperature. It absorbs 208 joules of heat. Calculate Q, W, delta U, and delta H for the process. First calculate the work, then calculate the initial and final pressures. All right, we work down through this. 208 joules of heat is going into the system. The total amount of energy is going up by 208 joules. So Q is positive. Let's get the description. The gas expands reversibly from 50 to 375 milliliters. it's absorbing 208 joules of heat. So this is why this is positive. It's absorbing 208 joules of heat. To calculate the work, you can use that equation 2.7. It's expanding. This is your VF over VI. It's expanding. That's going to be positive. The log of that is positive. The equation has a negative sign on it. So the work is negative 208 joules. So the delta U, the delta U equals Q plus W is 0. Okay, now from there, using Boyle's law to get your initial pressure and your final pressure. See what this looks like. It's going from an initial volume of 50 milliliters up to 375 milliliters. So we got those volumes. You got the moles. You can calculate the initial pressure. Again, assuming an ideal gas. And a final pressure. Remember, delta H equals delta U plus this. And that's the equation we're working with here. So we need this, what is the delta PV? It's the final pressure times the final volume minus the initial pressure times the initial volume. That's 0, so delta H equals 0.
What does delta PV stand for? Or like what? I'm kind of confused.
Yeah, I know. Before we had this,
Because it's not
that's work.
pressure. Oh, it's just pressure times volume?
Yeah, just pressure times volume.
Okay.
It's the change in that.
Change in the
Pressure times the volume.
But if it's an ideal gas, isn't it always 0? If you double the volume, you're getting
Half
half
the
the
pressure.
pressure. So pressure times volume is the same in all cases
For an ideal gas, yeah.
for an ideal gas. If it's behaving like Boyle's law. Oh, so it says as expected for what is basically a Boyle's law expansion. Delta H equals 0.
Yeah. I'm not so sure you would always get this delta U equaling 0 here. This part.
Because if you have work,
So you just specify a certain amount of going into the system. So you could specify any amount going into the system, then you would get 0.
yeah. It's because your work equals 0.
Yeah.
It's just coincidental.
Yeah, or the way that they set up
Well, yeah.
the problem. Right. Okay. Okay, let me give you a couple other things. I want to give you these 2 assignments, and we're going to handle them a little differently. Where I give you this. I want you to think, and this assignment, consider, well, let me get this in front of you. And I'm gonna allow you to address this one kind of as a class. Work on this together. Here's the way I'd like you to do it. I'd like you to, I hope there's a time when all five of you can kind of, you know, I don't know if you all have to split right after class or could come early on a particular class, but take a look at this. You can see you got kinetic energy, potential energy, pressure, volume, pressure times volume, temperature, initial or internal energy, enthalpy, heat, and work. Got a whole bunch of parameters there. And you got four, I wish there were 5 situations here. But I'd like you to just kind of do this as a class in a couple ways here. Number one, I want everybody to have a particular part that they focus on. You can discuss it and try to convince one another that this is what I think is happening here, there, and everywhere, what's happening to these different parameters. All you have to do is, let's see, which line is it on? Okay, about the 4th line down, it says fill in the cells with an I for increase, a D, a decrease, or no change. So you're not trying to calculate anything, just what direction are things changing, or is there actually no change? So look at temperature for a second. Why don't you toss out a couple here. Look at temperature. Find a situation where it's pretty obvious what the answer would be for temperature.
Any other ones that say isothermal?
Okay. Okay. So there are some that should kind of fall out pretty quickly. So if it's isothermal, T is no change. So kind of look for some of those things. Think about these. And you can collaborate with what I'm saying. Collaborate on, and the purpose of this is to be thinking through what's happening. We haven't said too much about kinetic energy or potential energy. We've talked about pressure and volume, temperature, internal, enthalpy, Q and W, so there's a bunch in here. There's probably some that halfway through here I may give you back 15 or 20 of these blanks filled in. So just kind of work on this for probably between now and next Monday. But discuss it, debate it, try to convince one another where you see discrepancies. No, I think that there's no work being done. Well, someone else thought work was being done. Discuss it. So that's the first assignment. I mentioned that we got this severe temperature thing coming in. I don't know if they're going to cancel school on Wednesday, but in case they did, I wanted to get a couple things in your hands. This is more, there is at least 1 or 2 more problems that I wanted to get in here, but I haven't chosen them yet. I wanted to get you something in there about heat capacities. And we'll talk about them, probably get over into that, talking about them Wednesday or Friday. So I may have another sheet that I hand to you with 1 or 2 problems on it. But there's 2 from the text, and they have the answers. And then number 3 is a favorite of mine. Oh, we haven't started talking about delta H of reactions, but that's what you'll need for number 3. We have talked about the calorimetry equation, which is first part of 3. And then we'll get into the delta H of reactions and the standard heats of formation and how to use them. Okay? Something you had in Gen Chem.
When is this homework due?
Probably next Monday.
Okay.
And I say probably, I mean, if we have class Wednesday and I have a few more questions, I'll give them to you Wednesday. If we don't have class Wednesday, then I won't get to them until Friday. So, but we won't do before Monday. All right?
Sounds good. Thank you.